Hey everyone, my name's Cassidy, and I'm going to be talking to you about superconductors. Superconductors have a wide variety of applications in science, such as in quantum computing, in magnetic resonance imaging, aka MRIs, and in particle accelerators, such as the Large Hadron Collider in Geneva, Switzerland. Superconductors were first discovered in 1911 by Dutch physicist Heike Kamerlingh Onnes. Onnes studied the resistance of solid mercury by cooling it down to cryogenic temperatures. He utilized the recently discovered liquid helium to cool the material down to 4.2 Kelvin. Prior to these observations, we knew that generally when running an electric current through a material, that as we decreased the temperature, the resistance also tended to gradually decrease with it. We didn't know, however, what would happen when we cooled these materials closer or near to 0 Kelvin. On April 8, 1911, Onnes observed that the resistance in his solid mercury sample abruptly disappeared. Following this revolutionary discovery, and some experiments that followed, we learned that superconductors have two main properties. A superconductor has zero electrical resistance and is perfectly diamagnetic. Diamagnetic meaning in the presence of an applied magnetic field. The net magnetic field within a superconductor is always zero. This property of magnetism in superconductors is called the Meissner effect. This effect causes a magnet to levitate above a superconducting material and is supported by the repulsion of the magnetic field. With these two properties in mind, there exists a critical, or maximum temperature, and a critical magnetic field where a material no longer is in its superconducting phase. In addition, there also exists a maximum current where a material can no longer be in a superconducting phase. These critical values are represented in the graph shown here. Up until 1957, with the introduction of the Barden-Cooper-Scheifer theory, or BCS theory, we still didn't understand why we observed these superconductive phenomena. BCS theory was theorized by John Borden, Leon Cooper, and Scheifer, and was published in April 1957 in the letter titled Microscopic Theory of Superconductivity. The trio went on to win the Nobel Prize in Physics in 1972 for this theory. To understand BCS theory, we need to be familiar with the properties of two types of particles, fermions and bosons. Fermions have half spin and follow the Pauli exclusion principle. There exists two fermions per energy state of an atom, with one spin up and one spin down, and as we add more electrons, we fill higher energy levels. Bosons, on the other hand, have an integer spin, are symmetric, and don't follow the Pauli exclusion principle, meaning many bosons can occupy a single energy state. At low temperatures, they typically stay in the ground state, known in BCS theory as the BCS ground state, and form a Bose-Einstein condensate. Bose-Einstein condensates demonstrate large-scale quantum behavior, such as a shared wave function. So exactly how do you get fermions to condense like bosons? Well, the central idea behind BCS theory is Cooper instability. Cooper instability is the arrangement of fermions made unstable in the presence of attracted coupling of electrons with opposite spin. These electrons form composite bosons and are called Cooper pairs. Electrons are attracted by the positive charges formed in an atomic lattice and is therefore indirectly attracted by the electron morphing these positive charges. Distances between a Cooper pair of electrons are relatively large, typically with 10 to the power of 6 electrons separating the coupled pairs of electrons. These Cooper pairs now behave like a Bose-Einstein condensate and move in sync along the superconducting material. Overall, this theory explains why type 1 superconductors have no resistance and why they also have zero magnetic flux. Type 2 superconductors, however, are a different story. So, what's the difference between a type 1 superconductor and a type 2 superconductor? Well, type 1 superconductors mainly consist of periodic elements, such as lead, mercury, aluminum, and they also require extremely low temperatures, relatively close to 0 Kelvin. Type 1 superconductors exhibit typical superconductor behavior. Type 2 superconductors are pretty interesting. They have two critical magnetic fields. Anything below its first critical magnetic field is not superconducting, and anything above its second magnetic field is not as well. Between these two critical magnetic fields, interestingly, the material enters what is called a mixed superconductive state. Within a type 2 superconducting material, there exists perfectly diamagnetic portions sandwiched between portions that have measurable magnetic flux running through it. The entire material, however, maintains a zero electrical resistance throughout every portion. When talking about temperature, type 2 superconductors also tend to have their superconductive properties at higher temperatures. What makes type 2 superconductors useful in certain applications is that its second critical magnetic field value is very, very high compared to the critical magnetic field value of a type 1 superconductor. For this reason, type 2 superconductors are preferred in many applications that need to operate under high magnetic fields, such as particle accelerators, which depend on the Meissner effect to assist fast-moving particles in making sharp turns. Considering all the useful properties of superconductors, the goal is to eventually create a material that can harness these properties at room temperature, since it takes up a lot of energy and resources to cool these materials to cryogenic temperatures. Accomplishing this feat and making it practical for commercial use could completely revolutionize the way we use energy. Well, just this year, in 2020, we got just a little bit closer to accomplishing that goal. In this 2020 experiment, condensed matter physicists compressed crystals made from carbon, sulfur, hydrogen gas, hydrogen sulfide, and methane, hit with a laser, and compressed the material between two diamonds at the very, very high pressure of 248 gigapascals. They found that the material had superconductor properties at the very high temperature of 287 Kelvin, or 14 degrees Celsius. In Fahrenheit, this would be 57.2 degrees. Obviously, due to the extremely high pressure and the complexity of making the material itself, it currently has no practical applications. Regardless, it's a huge breakthrough in the field of condensed matter physics. And maybe one day, we'll make a material around this temperature of 14 degrees Celsius that is commercially viable. Well, I hope you guys enjoyed this video. I had a lot of fun making this, and hopefully in the future we can learn just a little bit more about superconductors and find even more possible applications. I used some clips and some pictures to help me explain some of these topics, and I'll have all my resources linked down below.